Let's look now at direct memory access. So we have discussed interrupts, and now we know that the CPU can be working on something and let the controller of a device send a signal when something happens, like some output has been written to disk or some input is available for the CPU and so on. So there is an extra mechanism that also is supported by hardware that takes away even more job from the CPU when it comes to transferring large amounts of data to specific devices, and that is direct memory access. The idea is that if you have to transfer a big chunk of data from main memory to the disk, for example, since you have to send them in specific chunks, depending on what is the size of the buffers you have at the controller and the device to transfer data, having the CPU do this job would, even if it is optimized with interrupts, it would still consume time that the CPU can actually spend performing other, running other processes. So what happens in modern hardware is that you have a dedicated controller, that is the DMA controller, the direct memory access, that you can just think as an extra controller that takes care of transferring stuff from data from memory to devices or from devices to memory, and then notify the CPU when the transfer is complete. Okay, so it's an extra helper, if you want, at the hardware level that takes care of transferring data from the main memory to the devices in both directions, depending, of course, on the type of device. So basically, when you want to initiate a transfer using direct memory access, the host writes in a specific portion or address in memory that the DMA has access, specifying basically what information needs to be copied and what is the destination, and then the controller of the DMA takes care of actually doing the copy of the transferring of or the transferring of data. Okay, you need, of course, an unshaking protocol routine also when you want to coordinate with the DMA. This can be this is about, of course, the controllers that need to transfer data using the DMA controller, for example, a disk that wants to use the DMA controller. And also in this case, you have dedicated lines for requests and acknowledgement of the from the DMA controller. Okay, so I think the easiest is if I show you this image here. Okay, so let's say the CPU is running a certain process, and then at a certain point, it needs to transfer data to the disk, a big chunk of data to the disk. Okay, so this is step one. So what is happening in your computer in modern hardware is that the CPU will send a request to the controller to transfer the desired amount of data from a disk to the main memory. Okay. After that, the controller of the disk will actually coordinate with the DMA controller, the direct memory access controller here. Okay, and send the data to this controller. So basically, the DMA is now acting instead of the CPU when it comes to taking the data that comes from the disk and place that into memory at a specific buffer. Okay, so the DMA takes care of this work while the CPU is able to do other things, run other processes. Okay, it will take a while for the disk to for the controller of the disk to send the bytes to the DMA controller. And the controller will keep adding to the buffer here in the main memory until, of course, everything has been written to memory. Then the interrupt that is sent to the CPU to say, okay, the data you wanted from the disk is now in memory, will be actually generated by the DMA controller. Okay, so the CPU reaches the point in a process in which a system call says you need to transfer something from the disk, then the controller of the disk communicates with the DMA, so the CPU goes on doing other things, and the final interrupt that will create a context switch eventually, so that the CPU can go and start running again the process that was waiting for the data comes from the DMA controller in this case.